Hey, financial risk management guys. What I'm going to do now, this is a video for mathematically savvy for you, right? And once again, we're talking about regression. And what I want to talk about, right, is about the coefficients, about the distribution of the coefficients, about the distribution of beta, and about the distribution of alpha. So when we talk about, let's recall that beta is basically given by this formula, okay? And what we want to talk about, right, is that beta is also a random variable. Okay, it's because you can actually think about those things, right? We said that x and y are normally distributed, right? So what you can think about this is that you kind of simulate x, you simulate y, you calculate your regression, and you get a certain beta. Then you do it again, and you get another beta. Then you do it again, and you get another beta, right? So beta is also a random variable, okay? And the question is how beta is distributed. Okay? We want to know how beta is distributed, okay? So because we assume, okay, that that y1 yada 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 until yn are all independent variables, we can still apply the central limit theorem for beta, okay? And then what we're going to get that beta should be actually beta hat, right? The random beta is distributed like with sigma beta and with the expected value of beta. Okay. Now the expected value of beta is actually easy peasy, right? It's actually given by this. So what is going to be the variance of beta? Okay? That's where the difficulty lies, okay? Because if you have variance of beta, you actually have, sigma beta, right? So the question is how we can calculate the variance of beta, and how we do it, right? We're doing it actually a little bit tricky. So first of all, we're not calculating variance of beta directly. What we're going to calculate, we're going to actually calculate variance of beta conditional on x. Okay? It means that in this regression, we're assuming that x is actually constant, right? That the time series that we have for x are actually constant. And the entire randomness comes from epsilon and as well comes from y, right? So in this particular case, you can see that x is actually constant, and then you actually calculate, right? And then the calculation of beta, the variance of beta, actually goes to the variance of y, right? So then how do you calculate this beta, right? So in this particular case, you are going to use a definition, okay? So we know, what do we know about beta? We know that beta, right, is actually the expected value of xy minus the expected value of x times the expected value of y divided by variance of x. Okay? Okay, so the expected value of x times the expected value of xy minus the expected value of x minus times the expected value of y times the variance of x, right? So you can actually write it as follows. You can actually write it as a 1 over n, okay, xi times yi, I goes from 1 to n, say, because that's how you calculate it, right? Minus, and now you have the expected value of x times 1 over n, the sum of yi, I goes from 1 to n, and all this is divided by variance of x. So this is going to be, right, the expression for beta, for y, for beta, if you have this kind of time series, right? Now I'm not going into all these things, biased and biased estimator, right? For me, if you have enough observations, okay, and in the markets you usually have enough observations, all these things, right, are going away. They're important, okay, but but what I want to do is to do it quick and dirty, okay? So I don't care about too many mathematical niceties, and there are a lot of them. There are a lot of beautiful theory of how this all works. I'm not going to go into that. I'm just going to look on the bulk, on the meat of the calculation. So then, what you want to do, you want to take the variance of this. Now, because you assume that x is constant, right? This is going to be a constant variable. So you can take it outside. So what you're going to get the following. And you can take the 1 over n outside. So what you're going to get, now, this and this are going to go with a square. So you're going to get 1 over n square divided by the variance of x square. Variance square, right? So you take variance of x, square it. Variance of x times variance of x, variance of x, variance square of x, times, and now inside, right, you're going to get xi minus expected value of x times yi. I goes from 1 to n. Okay? Now, and then you need to put a variance here, right? So it's a variance of this guy. Now, this guy, right, is a constant. We assume, right, that xi are constants. So these guys are constants. Now, so then you can write this, right? You will be able to write this if you are going to raise this. Okay? You actually can write this as follows. You can write it as a sum of 1 over n square divided by variance of square x times, and now you're going to get here variance, right? Now, because yi are independents, I can actually write, if y, we know that variance of x plus y equals to variance of x plus variance of y plus 2 times covariance of xy. Now, because this is 0, right, because these are independent, I can actually write this as follows. This is going to be I goes from 1 to n, x variance of yi times xi minus e of x squared. Okay? Now, observe the following thing, that xi, the sum of xi minus e of x. Now, variance of yi is all variance of y, right? We assume that they have, now, and so xi times expected value of x, the sum 1 over n, is actually variance of x. Okay? So what you can do now, you can actually take this square, right? And you can take this sum, and you can declare it to be the variance of x. So at the end, what you are going to get variance of y divided n times variance of x, right? Because one square went with this xi minus cx squared, right? So hence, what you are getting here, right, that the sigma of this guy is sigma y divided by square root of n times sigma x. So that's all there is to it now. We will talk about the alpha next time. All right? Thank you very much and have a great day.